Okay, we are 4 minutes past the time, so we get started. So good morning or good afternoon, everyone. I'm really pleased to have my former colleague, Dr. Jian Tao, today to talk to us about the digital twin and wind energy. Uh, Jian has a very interesting career path. You know, he started as a physicist and then become an engineer. Right now, he's with School of Architecture as a specialist in visualization and digital twin obviously is one of the things people do in visualization. So with his richer background, he also collaborated with me and with other folks on wind energy applications. And so that's pretty much he's going to talk to us today. So welcome, Jim. The screen is yours.
Thank you so much. Sorry about the delay, and also thank Yuding for inviting me and to give a talk on the topics that we have been working on for the last several years. And let's get started. So let's see. How can I turn to the next page here? Okay, hopefully. I think I needed to start from the beginning. Just lost the control of the screen here for some reason. Let me go back to the second one. So I'll just make it easy for me to switch screens. I'll just go into this mode. So first, I'll talk a little bit about the Digital Twin Lab that actually is hosting all the projects I'll be going to talk about today, including the wind energy project. So the lab was started in 2022. And when I just joined the Department of Visualization as assistant professor, I proposed to start a lab on digital twin. And that's one of the first university level interdisciplinary labs that started at the Texas A&M Institute of Data Science. As Dr. Yudi mentioned, my background is computational astrophysics. My research was on binary neutron star and black hole simulations many years ago. And later on, I moved to Louisiana State because some of you know there was a LIGO detector, which was supposed to be detecting gravitational waves back then. No one knows when it will be detected. And that's why the career path is a little bit different for me. When I started working on that modeling work, a lot of time was spent on computational astrophysics, mostly on parallel programming, HPC. So gradually I shifted to computational domains. That's when I started looking for a position in this area. So I moved to Texas as a research scientist on high performance computing and data science. And then the story continued in 2021. I joined the Department of Visualization. And currently we are under the brand new College of Performance, Visualization, and Fine Arts, focusing on digital twins. That's my current research. So the beauty of digital twin is that it combines what we currently have in our college, which has one of the best visualization programs in the US. Actually, we have some top animation and game design programs. And then my background and also the collaborations I had in my last almost 20 years in my research career were mostly focusing on numerical modeling and simulation. It was a perfect match for me. So I started this PhD program, no, not me, so we started a PhD program on visual computing and interactive media. And I'm in charge of this digital twin initiative in this PhD program. And this lab was actually coming in time, perfectly in time. And we are trying to collaborate with the folks around the campus, not only engineering, but also agri-life and many other areas. As you may imagine, digital twin is really, really applicable to many of the digital transformation in manufacturing and many other fields. That's how everything got started. Actually, for us, it's about 3 or 4 years of effort just to put together this lab and all the research initiatives and some educational programs. So to me, digital twin is not new. I think it's probably to many of you who have been doing modeling and simulation, it's not something new. It's just like, a new brand, or you may call it a new paradigm. So from the data science perspective, I would consider a digital twin is a way for you to automate the data science process, starting by data collection to data cleaning, and then you try to do some EDA, exploratory data analysis, and then you do some modeling. Finally, you try to interpret the meaning of the results. And of course, the automation provided by digital twin goes beyond this. It can provide feedback loop for you to optimize your, for example, sensor deployment, a number of sensors and where they should be located, optimize your workflow. When you try to arrange different facilities to put together some manufacturing process or something like that. So it will be a kind of like a autonomous data science lab that you're building when you're after building digital twin. That's from my own perspective as a researcher. But if you put this in operational mode, this could be a very powerful way for you to automate a lot of things away. So essentially, it's a paradigm and a concept for you to automate the way how you do data science. Actually, if you think about in general, it could be a very decent way for you to do science in general. That's why there have been a lot of efforts in the research community to build self-driving labs, right? Self-drive labs. Essentially, you're building digital twin to integrate your lab equipment, automation, and also link to your modeling effort, and also link to your information collection and dissemination. So it's an automatic system to do science in some way. So there have been multiple definitions of digital twins online. If you do a quick search on digital twins, you'll see different groups, different consortiums, and different ways defined. But essentially, I think there are some common grounds of all those definitions. You need at least some representation model. You need some way for user to interact with the system. Otherwise, if it's running in a black box, how can you get information out from it? So there is always a user interface component in it. Be it a 3D model, or could be web-based, could be even command line interface. As long as you provide interfaces, it should be satisfying all these needs for the user interaction. Now, you also have a simulation mode, that a model that you need to be able to take the data you have and make predictions. That's all the power comes in when you're able to see something in the future based on the data you collected. You have the power to make changes, to make those bad things not happening, to make good things happening, to meet your needs. So between this modeling and also the physical sensors you deployed in your physical system, there will be always a cyber physical system that you need to deploy. You need sensors, and you need data streamed to your computer for processing, and you need a cyber infrastructure to hold the data and help you to analyze data and do some analysis, down the road. So you have a cyber physical system that connects your physical system and your digital system. So digital twin and physical twin, you need some communication between those. Now, this is a very simplified overview about what how a digital twin will be working between the digital space and the physical space. And sensors are the eyes and all the your eyes and ears for your system. So you need to make sure that you have the data that can be collected and streamed to you for the analysis and model building. And also you want to build a feedback loop. That's what this actuator in the physical space. In the physical representations, in most cases like switches, motors, and those things that you can control and provide feedback to the physical space. And of course, now if you think about it at a very high level, this could be robotic arms, could be even robots that you can send instructions and let it to interfere with the physical space. So again, automation is a keyword here. You want things to be automatic. And we don't put the human in the loop here, but in general, there will be some human components that you can provide interference to override, whichever this automation is going, or you can coordinate your effort from manual input and automatic input. So think of this more or less like a thermostat for your AC system. You can manually set your temperature. Of course, you can also automate the process. It's in a very, very similar way. It's just like the system could be pretty complicated if you have a systematic way to deal with the input data, modeling, and feedback, control, etc. when you build a digital twin, in many cases, you probably don't have the physical sensors ready, especially in the research area. When we are working on digital twins, we usually don't have the physical system available. Even if it's available, it usually take weeks, months, sometimes even years to get the sensors installed and deployed and get the data collected. And as you know, we have students work on this usually have 2 or 3 years, and the master students 5 years to graduate for PhD students. So we don't have I would say persistent layer of technical expertise that can provide this long-term support for operational running, at least in academia. So what we do, we took, in our case, we took the historical data as well as some, latest measurements data from publicly available as resources. We build a virtual sensors platform. So we mimic the way how the streaming data will be coming, and we just focus on our digital twin building. That's basically what we have been doing in almost all our projects for now, mainly because it's just, we don't have the time to wait for the real system to be up, at least for the academic research side. For certain applications, when we do have the sensors, we work closely with our collaborators to get the sensor data streamed in and process that in real time. And that's what we are working on in some of the projects, but most of the projects we're working on, we have to deal with all this synthetic data generation and also the virtual sensor platform to help stream the virtual data coming. But of course, if the protocol that we're using is shared among the virtual sensor platform as well as the physical sensor systems, we're all set in the sense that, for example, we have MQTT broker as our primary message passing system for streaming the data in and out. And all our virtual sensors are sending data directly as an MQTT message to certain topics. To the digital twin that we are developing and managing, it doesn't really care if it's coming from a virtual sensor or real sensor, because it's coming to the digital twin as an MQTT message, nothing more, nothing less. So when you have the real sensor coming up, it's fine. Just send your message to the topic that we have already created, or you can create your own topics. And then MQTT can handle the message passing between all these systems. So in this sense that, no matter if the virtual or real, you can mix them together and make it much convenient for us to work on the research project without worrying about the real sensor data, if it's ready or not. So on the implementation side, these are the systems we're using. We're using EMQX, MQTT platform, to collect the data and to send the information back for us. On the sensor side, we do have a lot of real sensors, physical sensors that we deploy and try things out in different areas. I'll show you some examples there. And in the back end, we use the TD engine, which is one of the, I think, a very promising time sequence database. And it's optimized, highly optimized for storing real-time data. And the latency is low, and it's performed pretty well. Of course, there are multiple other alternatives, but this is one we have been using, for the last several years. So based on the TD engine, which is a time sequence database, you can connect your dashboard, other things on top of that, without you doing extra work. It's just automatically connected through all their own APIs, and there have been open source community supporting all this integration. So all you need to worry about is actually on the modeling part, as well as the data sharing and other business intelligence systems that you build on top of this kind of system. So on the IT side, this is already working pretty well. So in our case, we create a Docker image, which is it's just like a container image. And whenever we want to run a system set, we spin it up. And we can just tell our user or our developer what your topics you want to share. It's kind of like a news group, right, for the MQTT to manage all the messages. Whenever we set a topic, for example, offshore turbine engine, and then everyone can send it to and subscribe to the topic. It's kind of like sending a receiving email, but with much less latency, smaller latency than the regular email. So with that, we can get the almost real time at a millisecond level message coming in and out, and it's very efficient. So we are pretty much set on this kind of setup for all our development work. Another big effort in the last couple of years in our group is to develop so-called surrogate models for the modeling effort. So most of the systems we have been dealing with, you are able to find theoretical frameworks to get started. That's the best scenario. In some cases, you cannot. It's just simply too complicated. For example, the medical system, there's almost zero theoretical framework for you to go directly from mathematical equations to all your final results. It's essentially a data-driven modeling effort. So in that case, it's relatively easy actually. So you just need to focus on your machine learning models or your model, whichever model you're building, heuristic models. As long as your model is working well, giving the input, predicted output, you're all set. You just use a model and put it in the background. It's able to back predictions. Whenever you get new data, you just need to update your model once in a while. This could be all done automatically. Now, with the series-driven models, it's a little bit different. You needed to figure out if this model is really a good match for your system. In most cases, of course, when you're working on the digital twin, you'll find a good series-driven model. For example, a computational fluid dynamics model or wind model or whatever, based on the physical equation, mathematical equations. That's what I'm good at. But the thing is that in most cases, those computation is really time-consuming. And as you'll see, some of the examples I'll demonstrate in the talk. I don't have time to demonstrate today for the full-scale simulation, but those may take hours and sometimes days. For some of them, or digital twin project we're working on, some take weeks on some of the best computers to run. And there's no way that you can provide a real-time feedback. And of course, the time scale and also the time frame for your project is highly depending on the requirements of your application. So probably for the backend model that can run for weeks, it might be working for you because your whole project span is probably years, multiple years. That's kind of different scenario that you want to consider. But in most of the cases, what we are trying to do here is to minimize the computational cost using surrogate models. And one of the most promising one that we have been dealing with in the last several years is using so-called reduced order modeling method. And I put some of the work we done, and since the slides will be shared with everyone, you can go there to look into the details. There's also a paper published recently with our previous postdoc who now moved to India as assistant professor. He led this effort to develop so-called hyper-reduced reduced order modeling method, which has been there in the community for a while, but we are currently trying to put together a package that can help us automate the process as much as we can. It's essentially a very, very time-consuming effort if you want to get into the physical equations, but there have been a lot of efforts trying to minimize the effort to reduce your modeling effort. Go from your full-scale high-fidelity model to a low-fidelity model, but with a certain uncertainty control so that you can have some results quickly with certain uncertainty quantification included. So with all that, we put together a digital twin development framework that have been used in multiple digital twin projects we have been working on. It turns out to be working pretty well for many of the projects we're working on. For different digital twin projects, we talk with domain experts, trying to figure out what kind of model they're using, what's their input, what's the output, what kind of user interface they are more comfortable with. And I would say not two digital twins are the same, because every time you're talking with different groups of users and application developers, they have different needs. And that's why we try to build a common framework so that as a digital twin developer, it makes us easier to plug and play, put all the components together. But for the users, we'll try to incorporate their models as much as we can in the system. So that's basically what we currently have. But again, there's still a lot of room to improve to make the whole process more smoother. So there is this is an ongoing project supported by the Institute of Data Science that we are working on the automated system to automate the prediction. So essentially, the idea is actually very simple. Given a physical system, no matter what, could it be a turbine engine, could it be some area with a fluid system running around. the first thing you want to do, of course, is to collect the data and make sure that, I'm talking about the pipeline, not the, you always start with your questions first, but you can start looking into the system deployment and development into where and when the sensors will be deployed. After that thing got, after that got figured out, these sensors should be able to, this sensor data should be able to give you a pretty good representation of the current state of the system. Okay, so where you deploy those sensors and how frequent those sensors needed to take the signals, send the signals back. There are a lot of information theory related requirements. For example, to resolve the frequency, resolve the dynamics of your system at a certain frequency, how many sensor data need to stream in will be more or less determined by Nyquist theorem. And you at least get 2 points collected within one period, right? The same goes for the spatial behavior. If you have a periodical behavior or some dynamic system you want to capture across a space, then you need to deploy at least 2 sensors to cover that period, right? So these are the very minimum requirements for you to deploy your sensors. But in most cases, it's not doable if it's, in reality. So how can you estimate the error you're introducing by deploying less sensors and deploying sensors at not too optimal locations? That's a very interesting and very important question. I think that both in academia and industry, people are interested in learning that. So assuming, that's something we're also working on with in collaboration with multiple research groups. But for what we are currently working on for this automatic forecasting system is to assuming that you have all the sensor data giving you a good representation of your current state of your system. Each sensor could be treated as a time series, each sensor data. And how to calibrate and register all the sensors in your system so that they are evolving forward using the time forecasting, time series analysis techniques and the forecasting techniques. You can predict what the system will be the next level. So again, not all the sensors are coming at the same, streaming the data at the same frequency. So you have to calibrate data, and sometimes some interpolations or extrapolation will be needed for you to move forward in your prediction model. But again, just like all the physical systems, for the nonlinear system, there's no way that you have a long-term prediction accurately. There are fundamental problems with all the way how the system got simulated and studied. But the short-term prediction it's actually doable, especially for mechanical systems. The short-term prediction, even for not so accurate model, you can forecast what the system will be in a relatively small period of time, given your data, historical data, is already covering some interested time frame. With that information, you can predict what the system will be in the next short period of time. So that's what we're focusing on. Actually, this turns out to be very, very powerful in the sense that you don't need to know anything about the system. This system will be able to provide, give you the full structure of what's going on. Now, think about this. If you have all the data, with the help of the latest, everyone knows larger models, this could give you a very detailed description about what system goes on. So using LLM, larger models itself, would be able to help you much unless you have a solid background information about the system is. And this sensor data plus some, modeling effort to help with the prediction and also linked to the knowledge graph and vector stores if you're building based on system you can have a very powerful, expandable digital twin, not can only predict, but also can provide a very good user interface for you to see what's in the future and what could be happening. And in most cases, the prediction, if you can go ahead in, for example, more than half a minute, larger models can give you some useful summarized information, mostly in time for you to see what's going on. And also, of course, this could be integrated into some automatic alert system and other systems and give you a good feedback. And that's, if you can build all this into a comprehensive framework, and all this could be linked together and help with automation, as I mentioned previously, this will be the fabulous, work. So again, we don't really care. That's the thing. We really don't care what data you are dealing with, as long as you tell us the physical range so that you can do quick check, and also the physical space about the units, so we can give you a good prediction about the system, and also give you some explanation about what's going on. So let's move back to the digital twin construction. We have digital twin representation models, and you also have the simulation models in the backend. You have data-driven models, signal-driven models. Both of them could be, used in your application depending on what kind of application you're dealing with. So lastly, is about cyber-physical system, and you need to get data collected with, some common protocols, and you need to have some actions and controls to provide feedback to the system. So that's the cyber-physical system that you need to concern for your digital twin you're building. So essentially, if you look at the cyber-physical system, it could be designed as a layered structure. At the bottom, we have devices, and you have gateways, get everything connected, and those needed to follow certain protocols. And then you have so-called middlewares. And now that's probably not a common word. People now call agents and other things to replace whatever middleware was doing. On top of that, you can build your application. So all this will be linked together as an integrated system to provide the information sharing and modeling and analysis system. So at the Digital Lab, we have multiple sample projects. I have just listed some of them here today, but you can click the link. I think it should be HTTPS. I forgot the S here. I'll update that later on. And then you can also scan the QR code to get to the website. So one of them is the so-called livestock farming system, and we are working closely with AgriLife folks here. It's one of the largest research entity doing all the agriculture-related research in the US, probably even in the world. We have some of the best researchers here in animal science that are interested in learning, how livestock farming could be automated. So they talk with us to build a digital twin for the system. This system got funded through USDA, the Department of Agriculture. They could give us some money just to build mostly for the hardware. We get all the sensors, and cameras, and feed log, sensors to detect how much food they are eating, and how much water they're drinking, etc. So all this could be built into a comprehensive digital twin system for them to monitor the cows. So in our case, this is is a research project. So we are focusing on the fenced, how to call farming. But in real life, if you are dealing with open range, it's completely different. You probably need to run drones. You get GPS signals collected. But in our case, we don't go to the tracking in that level. We use mostly computer vision-based techniques to track animals and check their status. More information could be found in the papers I listed here, and also in some of the links. Another project got funded by NIST, National Institute of Science and Technology, Standard Technology. We developed a digital twin for the disaster city, which is a training facility for first responders. And we have been working on this for the last 2 or 3 years. This is one of the flagship projects at our digital twin lab because it's got multiple entities at AM system got involved. We work closely with engineering folks and with the TEEX, which is Texas Engineering Extension Services. They're providing a lot of services and training and professional workforce development, etc. So we built a digital twin and with a very fancy front end based on the game engine. Some of you probably play 3D games. There's an Unreal Engine, which is very, very powerful. We use that on the front end to provide a user interaction for the training facility. So we build a 3D visual replica for the system, and that's how things got working. So this is another project that Dr. Yu Ding, me, and another professor in our college, Dr. Xudong Zhang, in our university. So we worked on an offshore wind energy system, but focusing on the human safety, workforce safety. So we try to estimate the ground force and other force reactions based on the gesture detection. We use motion capture systems. As you can see here in the picture, we put a pretty big wind just to simulate how wind could be. Of course, we cannot generate a very powerful wind from that fan, but it's actually give us some estimation about how that will be affecting the human gesture and the potential hazards that might be caused by not so safe procedures. So we carry out the modeling work and do the simulation using the OpenSync, which is used a lot by the musculoskeletal simulation community. We are using cameras to capture the human gesture and try to do a quick estimation about potential risks by using the full-scale simulation data and do a training the machine learning model and to make that predictions much faster. So we are working on 2 papers at this point, and hopefully we'll share some more information. I'll put that in the slides later on if you are interested in. So another system, I'm sorry, I think I'm almost running out of time, but I think it's good to let you know how wide the spectrum is for digital twin applications. It could be. So we got funded by Natural Science Foundation to build a digital twin for intelligent electromagnetic sensor system. What we are building, actually, the antenna system, the socket on the chip system itself is already pretty matured, system, and there's multiple already matured numerical simulation softwares that can do that. But what we are focused on here is one special piece called a memristor array, which is relatively new. Well, I mean, the idea was not that new, but the chip itself is relatively new. So we are working on some testing chips from a collaborator, and we are trying to build a physics-based modeling for what's going on inside this chip. So this is essentially an analog computing system, not like a digital computing system. It's an analog computing system. But this memristor array is able to simulate how neural network works by applying the voltage on different all the memristors in this memristor array. Usually it's 250 times 250 memristors. So you can apply the voltage and control the current by changing the resistance of the individual memristor. By doing that, think about the resistance more or less like the weight for your neural network. So you can map a neural network onto at least a part of your neural network onto a memristor. So you can do this analog computing before you convert everything into a digital space and share the information. And our focus is actually on this one, together with, of course, the rest of the system to make a whole digital twin system for design and testing validation purpose. So we just got started this year, and we are currently working on this one. So with all that, I think I still have some time to talk a little bit about the digital twin and wind energy. This presentation, the rest of the presentation is based on a recent paper published by through this collaboration led by Dr. Xukai Zhang, who is now a postdoc at MIT, and also in collaboration with Araj, one of my collaborators from civil engineering. He's also the supervisor of the Xukai. I'm in Xukai's committee, so we work together on this effort. So the motivation, of course, is essentially we know this offshore wind market is growing, and especially when you try to get deeper and deeper in the sea and try to extract more wind energy from the nature, more risks will be going along the way. So how to provide proactive modeling effort to give you some feedback before you passively receive the information from the wind farm. So the effort is trying to build this digital twin system so that we can get the information in real-time information and carry out analysis in real time, and then provide the decision supporting system that can give you a quick estimation about what the risk could be, what the potential cost could be for you to not only monitor the existing wind farm, but also deploy and find the locations where the wind farm should be located. Those could be analyzed based on the framework we are providing here. Of course, it's a research project. I don't think it's a good idea. If you are working on like a multi-million-dollar project, this will be something you'll rely on. It might be, not a good idea to get started. But again, let's provide a framework. Everything is open source. So it's provide a framework for you to take a look, to use this as a reference if you really want to, give it a try. So this is essentially a digital framework that we're building. We try to get the real sensor data from not only the whatever sensor collection, whatever data collection mechanism you're using. We are also collecting data from NOAA and other agencies, federal agencies and local state agencies about weather information for areas. We call it weather, but actually it's a long-term weather information we're collecting to understand the situation of the particular point of interest. And also, based on the model we're using, this called open. It's open PST. The model that we're using to study the based on the input parameter information and how the system will be reacting. So that information will be visualized and analyzed into using our surrogate models and provide feedback back to the system. So user can take a look at them, and then you can even integrate this into the marketplace to see how much a cost could be, for certain reactions. So for the testing system, we took one of those reference systems from NREL, National Renewable Energy Laboratory. This is a 5 megawatts. I'm sorry, it's probably it's a 30 megawatts OC4 system, semi-submersive OWT, is used for this testing. And so we took all the physical specs from that system and then integrated that into our modeling work so that we can have all the required physical specs and also information needed for modeling effort. I'm sorry, the system we use is called OpenFast. It started with a FAST system developed by NREL, and then they released this in open source, and also they turned that FAST, I believe version 8, into OpenFast. So that's a system people have been using to study to do the modeling work. To do that, we collect the wind information data. Again, since we don't have the real data coming from those sensors, what we do, we took the historical data from the NOAA website and mimic the way how system working at a certain period of time, historical period of time, and take the mean wind speed and also add some random wind spectrum and put everything into the open fast system. So of course, it's not just one simulation with different scenarios. We do this multiple simulations and give us a rough idea about how the system is working. So for the system decomposition, we do look into multiple potential fault, all the potential factors that can cause the system failure. So we use this fault tree for offshore wind turbines. And for different systems, this will be different, the weights will be different, but in this one, we focus on mostly 4 major components, like the tower structure, mooring and subsystem, and also the blades. Just in case something's failing, we're able to make some analysis, and based on that, we can predict the failing rate for the whole system. So this is the formulation that Xukai was working on based on the research work done by, I forgot, let me see the reference at the bottom, by Shen and Hong in 2021. And what we did, we took their formulation and added some extra specific requirements for our system. And also we are focused on the maximum of those anomalies, and based on those maximum values, we can predict the potential failing rate given the formulation here. So for the reliability assessment, the point of failure and also the probability of failure for different component of the system, we done the multiple Monte Carlo simulations using OpenFast. But again, as I previously mentioned, OpenFast itself, it's not really efficient. So it's very computational expensive if you want to run many simulations and to study the system, especially Monte Carlo simulation itself is not very efficient at all. you need a lot of simulations just to convert, give you some reasonable results. So after some warming up, and gradually you can see the system is converting to to some reasonable range. But the thing is that we cannot afford this for our real world scenario when we want to provide the real time feedback. So what we do, we build a surrogate model based on the OpenFast output, and basically we take the output from the OpenFast high fidelity model, and build a machine learning model based on the supporting vector machines, which is a very commonly used machine learning algorithm that people use to do the classifications and other problems. So we use machine learning model. This is actually based on the OpenFast output. We try to study different cases, but in one of the particular technique we mentioned in the paper that I shared previously is to use so-called SMOTE data generation. Essentially, it's trying to use a near neighbor, k-nearest neighbor method to generate the synthetic data near those failure scenarios, so that we can have a bit more data for that case. Of course, there are some overfitting issues, but this is give us some good magnification of the signal to noise ratio for certain special cases, so that you can have some representative data set for you to train the model to give enough focus or enough weight for those failure cases. We call as minority samples. So given all the information, we put together this decision supporting system for calculating the maintenance cost. But again, this is, I would say like hand-waving results, mainly because it's a highly dependent on various factors. But this one actually give you some framework for you to get started, to give you a rough estimation about potential cost for certain scenarios. If something happens, what could it be called? The potential cost for you to maintain the, put a certain maintenance shape and get something repaired. This method is also presented in the paper as well. So for the case study, what we did, we took the data from one of those buoy stations that you can find that from the NOVA website, and use that data as the weather information. We put it in our system and started this, put also using this virtual 5 megawatts OC4 submersive system, and try to put that into a digital twin system to study the system feedback. So essentially, the data set, particular part of data set we took is during the hurricane. So as you can see, the wind speed is pretty high in a certain period of time, and also the wave height is pretty high. So we use those to drive our system to see if our system is responding accordingly. So based on the incoming weather information as well as the specs of the OC4 platform, we got this output from our predictive model. And actually, it's working as expected. We definitely need more tests to do, but this showcases the response that the system is providing ahead of time, as predictive digital twin system is supposed to be working on, to be showing us. So with that, I'll point you all to the paper. You should be able to have access to the paper I shared. That's published in end of last year, but it should be in a volume in early 2026. So with that, I'll conclude my talk. Thank you all so much.
Well, thank you, Jian, for giving the talk despite the technical complexity at the beginning of the session. So I like to make a comment about the SMOTE method Jian mentioned in the talk. SMOTE was a method published about 25 years ago by the CS community. Sometimes I joke with my CS colleagues, SMOTE is one of the generative method, from the very beginning. It's just they generate a scatter data. It doesn't generate the image and text. But nevertheless, they create a synthetic minority data point, try to boost the presence of the minority and versus a majority ratio to make the anomaly detection or imbalance data anomaly detection more accurate. So that is a side note. So we still have about 10 minutes, and I'm wondering if any questions for Jen.
Maybe I can start. Thank you, Jen. This is very nice talk. In the Indiana's case, I just have a question about the failure mode. So out of many failure mode, you chose 3. Is there any specific reason you choose these 3?
So I think, again, we are using this more or less like a demonstration purpose. So when Xukai and Arash are working on this one, I think they started with 1 and then gradually added more just to start to leverage the system, whatever they can find. So it's more or less depending on the data they can find to do this analysis. But there again, Arash has a background in this structural analysis, so I think he probably also provided guidance for Xukai just to pick. Let's pick, those 4 with the data and also with all the tools we have. That's probably more comparable to some existing work. So I believe that's part of the reason. But again, I'm not expert on the structural analysis, but they, if hopefully. I can get you connected with the Xukai and Arash. They can probably provide more insight about the reason why they picked this 4 here, or 3. I'm sorry, it's yeah.
Any other questions or any comments?
Again, our lab is open for collaborations, and we are already concluded our 2 years of like incubation at Institute Data Science, and we are working with collaborators internally and externally to see if we can build some larger center with internal funding and external funding. So I'll be more than happy to talk with you if I have any interest to collaborate on any projects on digital twins. I'll be happy to see what we can help.
Thanks.
So Jen, there's a question in the chat. Yu Hao asked, when you study the human motions, which software platform did you use to connect inertial sensors?
That's a good question. So I believe it's that purchased. Let me go back to that project.
I believe it's in Shudong's lab, right?
Exactly. So that's in their lab. So they have some commercial solutions and also coming with the sensor system they purchased. So that's the very high fidelity motion camera data with a millimeter scale error, which is very, very good. But later on, at a later stage, when we try to build our own system, we are using cameras, just a single camera. There are some groups developing methods to use multiple cameras, but we are trying to do the single camera using a Google ML kit, machine learning kit, ML kit. If you search Google ML kit, there is a system that can generate biomarkers for people. If you the person in your image is able to automatically detect the biomarkers, it's not very accurate, but it will give you some information about the gesture and motion even, because they have a lot of biomarkers around the face and on eyes. So you can do a lot of things more than just simply get the motion system captured through this one single image. So again, the accuracy is a primary concern for that kind of system. But again, as you may imagine, if they get more and more data, when the camera getting better, I think this system will be continuing evolving. At some point, probably a single camera might be good enough for you to capture the motion information. That's our expectation. But who knows? There are multiple people are concerned about accuracy for that for now. But I think it's a good way to get started. Yeah.
Okay.
Sorry,
any other comments or questions?
Oh, yes, I have a question. So this is Fenglian Pan, and thank you, Dr. Jian Tao, for the great presentation. So you introduced many digital twin applications in cyber physics systems. I would like to know if you have some general insights about how to apply digital twin in autonomous vehicle area.
Yes.
Yes.
So we just published a paper recently about data collection. But again, autonomous vehicles, community is getting pretty big, and they already have robotaxis, other things already deployed. You probably heard about those news. It's many people I know, many researchers that started quitting that field, and they consider it's already a down, area. But on the research side, the system we're using is called CARLA, C-A-R-L-A. Probably heard about it.
Yes.
And it's actually also based on Unreal Engine. It provides a Python programming interface for you to interact with a 3D virtual system. So it's able to generate tons and tons of data in different ways. You can have a virtual LiDAR sensor, you can have a virtual radar sensor, and all different sensors generating data from that 3D environment. So it works pretty well as a data generator, which is actually very, very important for you to train your models for autopiloting and other things. And essentially, it's depending on how you look at the system, it's already a kind of like digital twin system, and you can integrate your sensor system. Assuming you're going to develop a new sensor or new machine learning model, you can integrate with the CARLA system. That's what we were doing for our auditory detection system, because no one has done anything about auditory things on a vehicle. That's what we were trying to do. Assuming you have a emergency vehicle coming around the corner, you won't be able to see it. No matter how good your sensors are, you won't be able to see it, but you can hear it. So for this special scenario, we developed an audio-based perception system, can detect those signals and give you early warning message. And there are a lot of things you can do with those kind of virtual systems. But as far as digital twin is concerned, you probably want to focus more on the data sharing and the communication. There is a team, Delaware. I forgot he was visiting us. What's the name? He's actually pioneer in edge computing. He's currently doing a so-called vehicle computing. He's a Chinese professor from Delaware. He's a department chair of the. I'm sorry, I forgot his name. It's on top of my head, but he has a lot of work in this area as well. And you can look at a lot of things his lab is doing. They are building various hardware and software integrated system, and it's very interesting work on that end. Yeah.
Okay. Yeah. Thank you.
So Jen, there's another question in the chat from Yuri. It's about what system do you use for storing and managing data? Object storage, SQL-like databases, graph databases?
Yes, in our case, it's mostly time sequence data for the sensor data. We do have a camera data, but those are stored just separately based on whatever camera system they're purchasing and using. So we are just use that as a whatever file system they're using. But for time sequence, we use a time series database called a TD Engine. You can do a quick search. TD Engine is developed by actually a startup a couple of years ago. Now it's getting bigger and bigger. Another very often used time sequence database is called InfluxDB. And there could be others I'm not familiar with, but those are the two top time sequence data time sequence database that you can look into. There are also various time streaming, time sequence data streaming platform like what's the name? I forgot the name, but we were actually looking into that. Those are both from the Apache Foundation software. Multiple open source systems are doing this real-time data streaming and archiving as well. They also provide online storage for you. For MQTT side, we use EMQX, which is an open source system, but they also provide online cloud system. You can pay a subscription fee and purchase those online storage. For some sensitive data, I would highly recommend that you can just set up a local server, and that will be just working perfectly fine. Whatever message you're sending through MQTT broker, you can choose to archive them or not. So that's your choice. If you choose to archive them, all the messages passing through your cyber physical system will be stored, and you can check them out later on. So essentially, that's what we are using for our digital twins. We don't rely particularly on any particular database systems or any content management system. Those are not crucial for get our system, digital twins running.
So Jian, one of the system you mentioned is Apache Kafka, right?
Yeah, Kafka. Yes,
Okay.
Kafka.
Okay. Yeah. So
Yeah.
you will follow up on that. Yeah. Okay.
Yes. Thank you.
Okay. I think we are right on time, and thank you very much, Jian, for coming to the series and talk to us about digital twin and your work related to wind energy. And we I'm going to post the video recording and your slides on Wind website. And next month we're gonna have Ahmad, my PhD student, talk about his experience participating in the cargo competition, which is going to end next week.
That's great.
So
That's great.
okay. So
Okay.
thank you very much for you all coming, and see you in a month.
Thank you.
Thank you.
Thank you.
Thank you.
Bye-bye.